Hello and welcome to the first lecture on Engineering Physics 2. Engineering Physics 2, the first chapter is Vector Analysis. In Vector Analysis, we will start the introduction of gradient, divergence and curl. Before starting this, it is important to know first of all what is the main objective of this presentation. The main objective of this presentation is to understand the concept of scalar and vector field, determine whether a vector field is conservative, find the gradient of a scalar field, find the divergence of a vector field, find the curl of a vector field. So these are the objective of this lecture. Now before it's come to the point gradient, divergence and curl, first of all it is important to know what is this first chapter, means what is this vector analysis. So of course vector analysis is a branch of mathematics that deals with quantities which have both magnitude and direction. Of course the question is come in our mind, if this is branch of mathematics, then why it is important to study this in the Engineering Physics 2 course. Actually in Engineering Physics 2 course, the second chapter is electromagnetism. This is completely based on vector analysis. So it is important to know first what are these vector notation and what are the physical meaning of this. Then we can apply this in our next chapter, that means electromagnetism. It is also important to know about the mathematics tool, because mathematics is the language of all the science or engineering discipline to explain. Means without the knowledge of mathematics we cannot explain any physical law. Suppose we say that I is equal to 0 in study of light. So I is equal to 0 is the mathematics, but its physical meaning is that the intensity of light is 0. And in more general way, that means for all common person, we can say that there is no light there is a darkness. So this is the mathematics, I is equal to 0. This is the physics, intensity of light is 0, and this is for common man, there is no light, there is a darkness. So of course this is the branch of mathematics. Still it is important to understand in the study of physics. But before again going to scalar and scalar of the gradient and divergence and curl, it is first of all important to know about the scalars and vectors. All the physical quantity can be divided into two parts, that is first is your scalar quantity and second is your vector quantity. Scalar quantity, that means these are those quantity having only the magnitude, that means no direction. And similarly we can also define the vector quantity. Vector quantities are those physical quantity which having both the magnitude as well as direction. The example of scalar quantity is the mass. As we know that mass having only magnitude, no direction. Similarly temperature and time, these are that quantity having only the magnitude but no direction. So these are the example of the scalar quantity. And similarly if we take the example of velocity and force and displacement, these are those quantity which having both magnitude and direction. So of course these are the vector quantity. Now if we come to our next slide, then we will see the scalar field and vector field. Right now we study about the is scalar quantity and vector quantity. So the area where the scalar quantity are effective, that area is called scalar field, and the place or the field where the vector quantity are effective, that is called vector field. So scalar field can be defined if at every point in a region a scalar function has a defined value, the region is called a scalar field. If at every point in a region a vector function has a defined value, the region is called a vector field. And we can understand, as we know that temperature is a scalar quantity because it has no direction, it has only magnitude. So if we study and if we take a rod and we heated it, then the distribution of temperature in the rod is the field, and that field is called scalar field. Why? Because temperature is a scalar quantity. Similarly, the example of vector field is the velocity field of following fluid. So velocity is a vector quantity. So of course the area where velocity is effective, that is called vector field. In next slide we can understood it more by seeing this example. Here in the first picture we see that air flow vector field means velocity of air we consider. So this whole is the vector field, and in case of second diagram, this is the scalar field because this diagram shows the variation of the temperature, and since temperature is a scalar quantity, so of course this area or this field is a scalar field. Now del operator. What is del operator? Actually del operator is main hero, we can say that, or this play a very important role in all this vector analysis. This is the main hero. So del or nebula is an operator used in mathematics, in particular in vector calculus, as a vector differential operator. This del is also called vector differential operator, and it is represented by, like we know the representation of triangle, so when we invert it, then this is the symbol of nebula. So here we see that it is also called the vector differential operator. Why it is called vector differential operator? We can see here in the next para the value of del. The value of del is I dou by dou x plus j dou by dou I plus k dou by dou z. This is the value of del. So this dou by dou x, dou by dou y, dou by dou z, this is, we know that the partial differentiation. So of course del gives the result as similar when we differentiate any quantity, and I, j, k is the unit vector, so of course it is a vector quantity. So that's why its name is vector differential operator. The coordinate x, y, z are the scalar field which are single valued function. Now come to the our main point, that is gradient of scalar field. As I already told in this slide, del is the main play a very important role in this chapter, and when this del operate with scalar quantity, then this gives you the gradient of scalar field, and when this del is operate with vector quantity with dot product, then this gives us divergence, and when the same del is operate with again vector quantity but with the cross product, then this gives us curl. So del is a single and it operates with gradient, and again it operates with the vector, but with vector it may be operated with the dot product or it may be operated with the cross product. When it operates with dot product, then this is called divergence, and when it operates with the cross product, then this gives us curl. So, and when this del operator operate with a scalar field, then this gives the gradient of a scalar field. If u, x, y, z is a scalar field, that is a scalar function of position r in 3 dimensions, then its gradient at any point is defined in Cartesian coordinate by grad u dou u by dou x I plus dou u by dou y j plus dou u by dou z k. It is usual to define the vector operator del is equal to I dou by dou x plus j dou by dou I plus k dou by dou z, which is called del or nebula. Then grad u is equal to del u. So del u is a scalar quantity, but when it operates with the del, then this gives the vector quantity. So gradient of any scalar field is a vector quantity. So this is the mathematics, but what is the physical interpretation of gradient? What does mean if we find out the gradient of a scalar field? It is very important to know about this, because when we know the physical meaning, then we can apply it only in the physics. So it is very important. So gradient tells how much something changes as move from one point to another. Gradient is multi-dimensional rate of change of particular function. Gradient vector is a representative of such vector which present the value of differentiation in all 360-degree direction for the given point on the curve. So this is the physical meaning of the gradient. It gives the maximum rate of change. So gradient of a scalar quantity is a vector quantity. It is clear when we find out magnitude of that vector quantity is equal to the maximum rate of the scalar quantity. So of course the gradient of any scalar quantity gives us the maximum rate of scalar quantity. Change the scalar quantity does not depend only on the coordinate of the point, but also the direction along which the change is shown. So the gradient always point in direction of maximum rate of change in the. We have seen that in our previous slide that del u is equal to dou u by dou x I plus dou u by dou I j plus dou u by dou z k. So if we move a small amount dr, dx is equal to dx I plus dy j plus dz k, the change in u is du is equal to dou u by dou x dx plus dou u by dou I dy plus dou u by dou z dz is equal to delta u dot dx, and when we divided it by ds, then we have du by ds is equal to delta u dot dr by ds, and here magnitude of dr is equal to ds. So dr by ds is a unit vector in the direction of dr. That means, which is already told in our previous slide, that grade u has the property that the rate of change of u with respect to distance in a particular direction d is the projection of grade u onto that direction. The quantity du by ds is called directional derivative. If in general it has different value of each direction and so has meaning until you specify the direction. That means no meaning if we not specify the direction. So this is about the gradient of a scalar field. Now come to our next point, that means divergence of the vector field. So this is the first role of del with the scalar field, which gives the gradient and which means that it gives the maximum rate of change. Now the second point is the divergence of a vector field. When the same del which operate with scalar quantity is operate with the vector quantity but with the dot product in between them, then the final result is called divergence of a vector field. When the del operator dot product with a vector field fxyz, we get a scalar value which is named as divergence. Then divergence of f is given as del dot f del fx by dou fx by dou x plus dou fy by dou y plus dou f by dou z. That means here we can see that no I, j, k. That means it is not a vector field but it is a scalar field. That means when we operate gradient with del, then this gives us vector, and when we operate vector with del but with the dot product, then the final result is of course divergence, and it is a scalar quantity, it is not a vector quantity. In hydrodynamics, a velocity fluid field that is divergence free is called incompressible. In the study of electricity and magnetism, which is the next chapter, so it is very important, a vector field that is divergence free is called solenoidal. Now of course come to our main important discussion, that is physical meaning of divergence. That is the mathematics. Now physics. What is the physical interpretation of the divergence? The divergence measures how much a vector field is spread out or divergence from a given point. Divergence is flux density, the amount of flux entering or leaving a point. Rate of flux expansion, positive divergence, or flux contraction is the negative divergence. Suppose we have the vector field and we want to know that field or that system is which type of system. That means either it is source or sink, or neither it behave as a source or sink. So how we can find out? If we try or if we are able to find out the divergence of that vector field and the final result, that means the divergence of that vector field result, we can say that this is sink, source, or it is neither a sink nor a source. If the divergence of any vector quantity is positive, that means that system is a behave as source. If it is negative, that means that system is a sink, or if it equals to 0, that means the system is neither source nor sink. So this is the exact meaning of divergence of any vector quantity. Now mathematically we can also prove it by considering a water flow which is denoted by AR, and the vector has magnitude equal to the mass of water crossing a unit area perpendicular to the direction of a per unit time. Now take a infinitesimal volume element dV and figure out the balance of the flow of in and out of dV. To be specified, consider the volume element dV is equal to dx dy dz in Cartesian coordinate and think first about the face of area dx dz perpendicular to the y-axis and facing outwards in the negative y direction, that is the one with surface area ds is equal to minus dx dz j. The component of vector A normal to this face is A dot j minus ay and is pointing inwards, and so its contribution to the outward flux from the surface is A dot ds is equal to minus ay y dz dx. This is the figure. A similar contribution but of opposite sign will arise from the opposite faces, but we must remember that we have moved along y by amount dy, that this outward amount is ay y plus dy dz dx minus under bracket ay plus dou ay by dy close the bracket dx dz. So the total outward amount from these two faces is dou ay by dou y dy dx dz minus dou ay by dou y dv. Summing the other faces gives a total outward flux of dou ax by dou x plus dou ay by dou y plus dou az by dou z under bracket dv is equal to delta dot a dv. The divergence of vector field represents the flux generation per unit volume at each point of the field. Divergence because it is an efflux, not an influx. Now, this is about the divergence of a vector field. Now, come to our next important thing, that is curl of a vector field. We already discussed about the gradient, in which del is operate with a scalar quantity. Then we discussed the divergence, in which the del is operate with a vector quantity but with the dot product, and its physical meaning is that it gives how much quantity is diverge or contract in any system. Now the next important is the curl. In divergence, del is operate with the vector quantity. In curl, again this del is operate with the vector quantity. The difference is what? In the previous case it operate with the dot product, but now these two vector quantity, that means del and the vector quantity, is going to operate with a cross product, and the resultant is called curl of a vector quantity. Why it is called curl? Because the reason for the name curl is that the curl vector is associated with the rotation. As its name clear, that curl, that means something rotation. So since it associated with the rotation, that's why name is given curl. When the del operator cross dot product with vector f, it gives the vector value which is named as curl. Then curl of f is given as del cross f under big bracket, or we can say that it is the matrix form ijk dou by dou x, dou by dou y, dou by dou z, and after that pqr. So this equals to dou r by dou I minus dou q by dou z I plus dou p by dou z minus dou r by dou xj plus dou q by dou x minus dou p by dou I k. That is equals to curl f. So come to the main thing, that means physical meaning of curl. If curl f is equal to 0 at a point P, the fluid is free from rotation at P. If f is called irrotational at P, if curl f is equal to 0, A teeny paddle will move with the fluid but does not rotate about its axis. If curl is not equal to 0, the paddle will rotate about its axis. So this is about the physical meaning of curl. Now, to understand more about this, or for remember, we can also understood it in the other way. The curl means rotation. So if we find out the curl of any vector quantity is equal to 0. Equal to 0, 0 means no. 0 means we have nothing. So if we have the value curl f is equal to 0, that means that vector quantity, suppose here we take the curl f, so f is a vector quantity. If curl f is equal to 0, it means that f is not a rotational vector, it is a irrotational vector. Okay, it is a irrotational vector, it is not a rotational vector. And if curl f is not equals to 0, it means that it is a rotational vector. If f is equal to 0, 0 means nothing, no, it means that it is a f is a irrotational vector. And if f is not equals to 0, it means that f is a rotational vector. So we can find out in this way, or we can remember in this way the meaning of the curl. The use of this curl, we can also understand that in the other way. In magnetism, if we have magnet, then we know that any magnet having two poles, north pole and south pole, if we break this magnet from its middle, now we have the two magnet, but again both the magnet having the north pole and south pole. If we continue this process 100 times and we have suppose n number of magnet, and then each magnet having the north pole and south pole, it means that in case of magnetic field, in case of magnetism, there is a no meaning of single pole, always having the dipole. So in other words, we can say that if the magnetic line of force originate from a one pole, then definitely it will be going to terminate on the another pole. So in this way, the total outward magnetic flux is 0. So magnetic flux is 0. That means here we can use the curl. That means why? Because here this form a rotation. The magnetic line of force originate from one pole and terminate on second pole. So it make it complete a rotation. So here we can use the curl of magnetic field. So this is about the gradient, divergence and curl. Now come to the properties of gradient, divergence and curl. In case of gradient, we can see here there are two terms, psi and phi, and A and B. Psi and phi, since we always take gradient, or with the gradient, that means we always operate del with the scalar field. So of course here psi and phi are the scalar field. So when we have two scalar function psi and phi and we add it and then find out, or then we operate with the del, then it gives the del psi plus del phi. Sorry, it mistake here, it is not written here del phi, but it will be del phi. Now in next, when we take product of these two scalar quantity del psi phi, then this will be equals to phi del psi plus psi del phi. Third point is, or third property is del under bracket a dot b is equal to under bracket a dot del b plus under bracket b dot a B dot del A plus A cross del cross B plus B cross del cross A. If we see the first two equation, then it is exactly same as when we find out the differentiation of any two function when it is added and when it is multiplied. So that's why the del is called the differential operator. In the next is the property of the divergence. A and B are here the vector quantity, psi is the scalar quantity. So del dot A plus B is equal to del dot A plus del dot B. Del dot psi A is equal to psi A dot A plus A dot del psi. Del dot A cross B is equal to B dot del cross A minus A dot del cross B. Curl properties. Del cross A plus B, A and B are the vector quantity, is equal to del cross A plus del cross B. Second, del cross psi A is equal to psi del cross A plus del psi cross A. Del cross A cross B is equal to A del dot B minus B del dot A plus B dot del A minus A dot del B. These are the distributive properties. Del psi plus phi is equal to del psi plus del phi. Del dot A plus B is equal to del dot A plus del dot B. Del cross A plus B is equal to del cross A plus del cross B. So distributive properties are those property when we take two scalar in case of gradient and two vector in case of divergence and curl, and we add it and then find out the gradient, divergence and curl. So these are called the distributive properties. Product rules, again it is same which we already studied in the properties of gradient, divergence and curl. When we multiply two quantity and take the divergence, gradient and curl of this quantity, then these are called product rules. And the last one is content rule, in which we take we find out the gradient of product of two scalar quantity, divergence of product of two vector quantity and curl of the same. Then this will be del f by g is equal to g del f minus del g f by g square. Del dot a by g is equal to g del dot a minus del g dot a by g square. Del cross a by g is equal to g del cross a minus del g cross a g square. So these are all about the gradient, divergence and curl. So summary, we discuss about the divergence, gradient and curl. In case of gradient, we operate del with a scalar field. In case of divergence, we operate vector with the del operator with the dot product, and in case of curl, we again operate del with a vector quantity but with a cross product. So when we find out the gradient of any scalar quantity, it gives us vector. When we operate divergence of any vector quantity, it gives us a scalar. Or the result which is obtained by curl of any vector quantity is again vector. Physical meaning, in case of grade f, the direction in which f changes most rapidly. Divergence f, density of flux, that is the fluid velocity per unit volume. And curl f is spinning flux affecting on the virtual surface. So now here we completed our first lecture on engineering physics 2, that is vector analysis, and in vector analysis we discuss grade, divergence and curl. So now again we will meet in our next lecture, which is on line integral, surface integral, volume integral, and then relation between them. Okay, thank you so much. Have a nice day.